All right, so the last category of identities that we want to look at here are what we call half-angle formulas. And just like how we started with these things called double angle formulas, where the angle looked like 2x or 2 theta, something that was being doubled, as the name suggests. In this case, we're looking at things that represent an angle that's been halved, so alpha over 2 instead of being multiplied by 2. Okay, and again, we're going to use the work we've already done to develop these. So we're specifically using the reduction formulas that we just came up with. Take a look at the first reduction formula that we found. Sine squared of x equals 1 minus cosine of 2x over 2. Oftentimes, at this level of math and higher, it's really, really helpful to do what's called a variable substitution. We have a variable here, the x, but to put things in the form that we're ultimately looking for, we're going to set x equal to a different expression involving a different variable. I'm going to let x equal alpha over 2. This is just defining a new variable alpha that relates to x in that specific way. The benefit of this is if I were to substitute now the alpha over 2 in for the x's on either side, then here the x becomes alpha over 2. It looks like a half angle, and that's what we're trying to get, a half angle. If I plug alpha over 2 into this side, 2 times that, the 2 is going to cancel the 2 in the denominator and just leave me with alpha. Okay, so we're making that replacement gives me this. Now, this is sine squared, so I really need to take a square root of both sides. So I'm just looking at a sine of alpha over 2 on the right-hand side. If I took a square root of both sides, it's really important to remember that anytime you take a square root of both sides of an equation, you're supposed to be putting this plus or minus here. But this gives me my half-angle formula for the sine function. Sine of alpha over 2 equals plus or minus the square root of 1 minus cosine alpha over 2. We could follow similar steps to derive half-angle formulas for the cosine and the tangent function as well, which are shown here. Now, notice for tangent, there are 3 different half-angle identities that you could use, and we're not really going to use these last 2. I mean, you technically can, but I'm going to be using this one here because this one follows the most directly from the 2 above it. These you can derive from this just by, proving a trig identity, basically. Yeah, one thing I wanted to point out also, which you'll see in the examples that we're going to do, the plus or minus here makes this a little bit different from the other identities we've looked at, the other formulas. That means there's technically 2 different expressions on this right-hand side, one that's positive and one that's negative. Typically what's going to happen is if you're using a half-angle identity or a half-angle formula in an example or some problem that you're working on, you have to use the information given to you in the problem to determine which of those 2 applies to that particular case. Do we want a positive or do we want a negative? So you'll see what I'm talking about in the second example that we do here. First thing I want to do is evaluate tangent of 15 degrees. 15 degrees is not something that shows up on our memorized unit circle. Obviously, we can take a tangent of it, but I don't want to just plug it into a calculator. If you did that on a test, you would get 0 points for that, because I don't care that you know how to push buttons on a calculator. I want to see that you understand what's going on here. 15 degrees. Even though it's not an angle that shows up on my memorized unit circle, it is half of an angle that does show up. 30 degrees divided by 2. Okay? 30 degrees, I know the tangent of 30 degrees. That's root 3 over 3. But by putting it in this form, that 30 degrees up there is like the alpha that's appearing here. So 30 degrees is going to be used in my half-angle formula for the tangent function. Now, for tangent, our half-angle formula, and again, remember we had 3 of those, but our half-angle formula looks like 1 minus cosine of alpha, which in this case is 30 degrees, over 1 plus cosine of alpha. Again, that's 30 degrees. Okay? both of these I know the value of. They're both equal to root 3 over 2. Now notice I didn't put the plus or minus here. I could have put that, but I want to narrow this down to either a positive or a negative. And the trick is to think about what it is you're evaluating. Tangent of 15 degrees. Which quadrant is 15 degrees in? Well, 15 degrees would definitely be in the first quadrant where tangent is supposed to be a positive function. So the result of this should come out to a positive number. Therefore, I want the positive square root, not the negative square root. That's how we make that determination. Let's work this out. This is equal to the square root of 1 minus root 3 over 2 over 1 plus root 3 over 2. Now, I could, I guess, technically leave it in this form, but this is very far from being simplified. So what I'm going to do is start by clearing out these smaller denominators, these 2's. I can multiply by 2 over 2. Distributing the 2's, I'm going to get 2 minus root 3 over 2 plus root 3. And I suppose I could also just leave that as is, but I'd like to rationalize excuse me, this denominator right here. So I'm going to do that as well. How do you rationalize a denominator of this type? We multiply by the conjugate, 2 minus root 3 over 2 minus root 3. This is something you talk about in algebra. Why do we do that? Well, we do that because the product of these two things would look like a difference of squares. 2 squared minus root 3 squared, or in other words, 4 minus 3. So this becomes the square root. My denominator becomes 4 minus 3. Of course, that's just equal to 1. Over, and then this I have to actually multiply out. That's going to look like 2 times 2, which is 4. Negative 2 root 3 minus 2 root 3. That would be minus 4 root 3. And then negative root 3 times negative root 3 is positive 3. Okay? My denominator becomes a 1, and if I take the square root of 1, it's still just 1, and so I can kind of just ditch the denominator completely. I'm really just left with my numerator. 4 plus 3 is 7, minus 4 root 3. I can leave that in that form. I think I'm satisfied with how that looks. Okay? There's other ways of going about simplifying that, so that, I could approach that in a different manner, but I think that's a perfectly valid way to leave that answer. Notice we have a radical within another radical here. That's very common when doing these half-angle formulas. You're probably going to see a decent amount of that. One last example, then we can call it a day on this section. Given that tangent of x is equal to 3, and it says in quadrant 3, so specifically it means the angle x is in quadrant 3. We want to find cosine of x over 2. Okay, so how are we going to do that? For cosine of x over 2, we need a half-angle formula. Cosine of x over 2, we know, is equal to, again, plus or minus, but I'm going to hold off on putting that plus or minus for a second. 1 plus cosine of x over 2. That's just using our half-angle identity directly. And like I said, we're going to wait for a second before we decide whether this should be positive or negative. Let's now see if we can determine anything useful about our x here. So tangent of x equals 3. Okay. I'm going to use that technique that we used previously and try and sketch that angle. So that angle is called x as a reference angle in quadrant 3. Now, if tangent of x is equal to 3, 3 is the same thing as 3 over 1. So I could call that, if I'm thinking of this in terms of opposite over adjacent, 3 and 1. Except, as before, both of those should be negative because of where they are. Pythagorean theorem would help me get this guy right here. So that's 9 plus 1, which is 10. Square root of that is root 10. All right. With that said, can I find cosine of x? The cosine of x is adjacent over hypotenuse. So negative 1 over root 10. Or if I were to rationalize, that's negative root 10 over 10. So cosine of x equals negative root 10 over 10. And so that's what I'm going to be able to put in here. But then the next thing I'm supposed to determine is whether or not we're looking at an angle, whether or not this is supposed to be positive. So what I'm going to do is take what we're given, tangent of x equals 3, and we're in quadrant 3. And I'm going to set up an inequality for x. If x is in quadrant 3, then that means x is greater than or equal to pi, but less than or equal to 3 pi over 2. That's like the boundary for the third quadrant, right? Now, think of what it is we're trying to find, cosine of x over 2. Notice, I don't want to just immediately say that this is negative because x is in the third quadrant. Yes, cosine of an angle in the third quadrant should be negative, but x is the angle that's in the third quadrant. X over 2 is a different angle. That could live somewhere else. And so we're going to try and determine roughly where that is. If x is between pi and 3 pi over 2, then x over 2, I can get an x over 2 here by dividing everything by 2. Pi over 2 is less than x over 2, which is less than 3 pi over 4. Okay? Think about where that is. Pi over 2 is here. 3 pi over 4 is here. Everything between pi over 2 and 3 pi over 4 would be in the second quadrant. So this means x over 2 is in the second quadrant. Okay? Because all of the angles between pi over 2 and 3 pi over 4 are in the second quadrant. Cosine should be negative there. So with that said, I know that we want a negative out here instead of a positive. What next? That's equal to negative square root of 1. And again, we found cosine of x. It's negative root 10 over 10. So let's say minus, since it's negative, root 10 over 10 over 2. Now I want to multiply my numerator and denominator by 10 to clear out that denominator. So this is going to equal negative square root of 10 minus root 10 over 20. Okay? I'm going to leave my answer in this form. Technically, I could rationalize this because I would be taking the square root of my numerator and my denominator, but I don't really see the harm in just leaving my answer in that form. Okay? That's going to wrap up section 9.3.